Hello, welcome back. In the past few videos, we've been talking about some integral tests. We want to find out if a series converges or if a series diverges. We've talked about the nth term test, we've talked about the geometric series test, and we even mentioned the telescoping test. But today we're going to take a look at what happens if those tests fail. And one option we have is something that we call the integral test. Now, the integral test, not necessarily the most friendly idea, but the friendly of our tests, but it does give us a very powerful idea that we can compare integrals, or the series that we're looking for, and we can compare them to integrals. And we're going to talk about that we're going to talk about that as we go through these examples. So this is what the integral test says. Suppose that for all x greater than or equal to 1, which is typically what's going to happen, a function is if the function is continuous, positive, and decreasing. Now, what decreasing means, basically that the values are getting smaller. Now, that means as we go on forever, the values are going to get smaller. Now, when we say decreasing, we don't really mean immediately. We really are saying as n goes to infinity. So we could have a function that bubbles up, but as long as n goes to infinity, as long as those values get smaller, we can use this integral test, even if there is a bubble. That's very useful for us. Now, what the integral test says that if I'm looking at a series, then I can compare it to an improper integral. Now notice, this will be an improper integral. We'll talk about that in a second here, okay? But, integral, there we go. Can't spell integral today. So, if I'm looking at a series, as my sequences go from 1 to infinity, I can compare this to my integral as the values of the function go from 1 to infinity. And here's what the big rule is. It says this: if either diverges, so does the other. If either converges, so does the other. And this is really nice because it tells us if the integral we solve converges, then the series will converge. If the integral diverges, the series will also diverge. So we say that the series and the integral go hand in hand. Right here. So let's look at an example. Now, the first thing we have to check, determine whether the following series will converge or diverge. So I'm giving this little example right here as n goes from 1 to infinity. Now, this is not geometric. It's not my geometric form. I can take nth term, let n go to infinity. As n goes to infinity, we get 0. So nth term fails. This is not nth term. Remember, nth term says if it equals 0, we have to use another test. So it's not geometric and it's not nth term. So we only have one option today, and that is our integral test. So first thing I'm going to do is I'm going to write this out as a new function. Let f of x equal 1 over 3x plus 4. And now for the part that most people hate. You have to say that this function is continuous if x is greater than 1. So if I let x be greater than 1, there are no domain restrictions if x is greater than 1. Remember, my domain restriction is going to be negative 4/3. The function is continuous, always going to be positive, and as x gets larger, the values get smaller. So we're going to say that. We're going to say that the function is continuous, positive, and decreasing. You must say this. Alright, so what are we going to do next? Well, because it's continuous, positive, and decreasing, we can now use the integral test. So let's go ahead and do that. We're going to write our new integral from 1 to infinity, 1 over 3x plus 4 dx. Now you might remember, this is improper, so I'm going to write this, the limit as b goes to infinity, 1 to b, 1 over 3x plus 4 dx. Now notice I use x here, they use n here. N is denoting this is a series. X is just saying that, hey, look, this is a function right there. So that's really the only difference. If you use n dn, honestly, the AP will just say, hey, look, they misspelled x. All right, so I can integrate this. We get the limit as b goes to infinity. Remember, this is going to be a u substitution. My du is going to be 3dx. That's telling me I'm dividing by 3. And this becomes natural log of 3x plus 4. And that's going to go from 1 to b. And of course, I can do this. Take out the 1/3. It's just a constant. Limit as b goes to infinity. And I can just plug this in. We get the natural log of 3b plus 4 minus the natural log, plug in this, of 7. Can't see that. There we go. Minus the natural log of 7. And if we let b go to infinity, what happens to this? Well, what's infinity minus any numbers? Just infinity, right? So this is going to equal infinity. So since infinity is not a number, this will diverge. So we would say the integral diverges. You can abbreviate. Therefore, the series diverges by the integral test. You can abbreviate that a little bit. The integral test. So if the integral diverges, the series will diverge. And there is our answer right here. Now be careful, look how I wrote it. The integral diverges, therefore the series diverges by the integral test. You're going to be able to do almost all of these in your head, but you want to make sure you show your work. And also don't forget to put this down at the beginning, right here. The integral test is by far the longest of the tests that we will learn, but it is an important one because of this idea that if you can find out the series, you can find the series converges, diverges by looking at the integral itself. All right, so let's try this one. Okay, we want to go from 1 to infinity. Okay, so again, this is not geometric. It looks geometric, but it's not geometric, and it is not nth term. So I'm going to use my integral test. I'm going to let f of x equal 1 over x cubed. And this is positive, continuous, oops, can't spell continuous, continuous, and decreasing. So you have to write this down. Check. So what are we going to use? We are going to now use our integral test, and we're going to go ahead and write this out. The integral. And I'm just going to write this as x to the negative 3 from 1 to infinity. Be careful, this is a 2. 2 to infinity. dx, don't forget your differential. And again, improper, so I'm going to write this out as the limit as b goes to infinity, 1 to b, x to the negative 3 dx. And integrating this, let's see here, we get the limit as b goes to infinity. Be careful, you're going to add 1. So we're going to get, excuse me, negative 1 over 2 x squared from 1 to b. And we're going to plug in equals, using the fundamental theorem as b goes to infinity, negative 1 over 2b squared plus 1 over 2. Plug in infinity, this becomes 0 now. And so what we're left with is just 1/2. Now, danger, Will Robinson, danger. Okay? Right here, I want to take a look here. This does not mean this does not mean the series converges to 1/2. It does not mean, sorry, can't spell mean. This does not mean the series converges to 1/2. What it is telling us is that the series will converge. And a lot of times we won't know what it converges to, and that's very common in mathematics. All we want to know is, will the series converge? We don't know what it will converge to, but we know at some point, if we go on forever, if I add up an infinite number of these, like this would be like 1 over 1, 1 plus 1/8 plus 1/27 and on. If we go on forever, this will converge. Do we know what it converges to? No. The integral converges to 1/2. That does not mean the series converges to 1/2. All we know is the following. The integral converges, and you can abbreviate, the integral converges. Therefore, the series converges by the integral test. And that's all that means right there. That's all it means for us, okay? We just know that the series converges by the integral test. If you say the series converges to 1/2, you will get that wrong. Okay, all right, go to part 2 and take a look at a really cool application of the integral test in order to approximate the value of a function, of a series.